Hello everyone, my name is Haitao Wang, and today I will be presenting on the topic Approximate allocation for vertical games. The presentation will be divided into three parts: the background of the problem, the research methods and the key results, and the further work. Let's begin with the first part, the background. In cooperative game theory, there are generally two types of problem: profit distribution and cost sharing. Let's take cost sharing game as an example. A typical cost sharing game can be represented by a pair NC, where N is the set of players and C is a characteristic function. The characteristic function maps any coalition of players to a non-negative real number, presenting the cost generated by that coalition cooperating. Now, an important question is how to fairly allocate the total cost to ensure the stability of the grand coalition. Means that no smaller coalition will break away from the grand coalition to cooperate on their own. Next, let's introduce an important concept in cooperative game theory, the core. The definition of the core is as follows. The distribution vector is in the core if it satisfies feasibility and coalition rationality. Feasibility means that the total cost generated by the ground coalition must be fully allocated among the players. Coalition rationality means that the cost allocated to any smaller coalition should not exceed the cost they would face by breaking away from the ground coalition and cooperating on their own. We can see that this concept is attractive because under the current allocation scheme, based on coalition rationality, no player will have the incentive to leave the coalition. This motivates all players to participate in the ground coalition. However, in many types of games, the core may be empty. So, in 1993, scholars introduced the concept of the approximate core, which relaxes the condition from the core. This definition ensures that the total cost generated by the ground coalition is fully allocated, and that the cost allocated to any smaller coalition will not exceed alpha times the cost they would incur by breaking away from the ground coalition and cooperating on their own. We refer to the value of alpha in second inequality as the approximation. Clearly, when alpha is large enough, the approximate core always exists. However, the smaller the alpha, the better the allocation scheme. Therefore, finding the optimal approximation ratio is crucial. The problem we are studying is minimum vertical game. In this game model, the set of players corresponding to the edge set of a graph. The cost generated by any coalition is the weight of the minimum vertical of the subgraph induced by the subset of edges. The core of the minimum vertical game can be empty. Let's illustrate this with a simple example. Consider the following graph, where each vertex has a weight of 1. There are 3 players, E1, E2, and E3. Clearly, the code generated by the grand coalition is the weight of the minimum vertical of this graph, which is 2. Now, let's assume that the core is not empty. According to the definition of the core, this must be distribution vector Z that satisfies this system of inequalities. But obviously, that leads to a contradiction. Therefore, the core of the minimum vertical game can indeed be empty, making it important to study its approximate core. Okay, let's move on to the second part, research methods and key results. First, we present the integer programming formulation, the relaxed programming formulation, and their duals for the minimum vertical problem. A simple case is when the integrated gap of the linear programming is 1, in which case the optimal values of the 3 formulations are equal. This means that the optimal value of the dual program is also the total cost, and the optimal solution of the dual is the allocation vector we are looking for in the core, which is easy to verify. However, when the integrity gap of the LP is not 1, meaning that the optimal value of the dual cannot be taken as the total cost, we investigate this case. Here is the definition of the integrity gap. Using the integrity gap of the linear programming, we prove theorem 1, which is one of our main results. We prove that for a specific instance, the ratio of the optimal value of the integer programming to the optimal value of interrelated programming is the optimal approximation ratio. This ratio, as a coefficient multiplied by the optimal dual solution, gives the vector in the optimal approximate core. However, the allocation we construct in theorem 1 cannot be obtained in polynomial time, because solving the minimum vertex cover problem is NP hard. Therefore, we continue our work with the goal of designing an algorithm that output an allocation in the approximate core in polynomial time. First, we want to start by studying the optimal solution of the linear programming. We first give the definition of a half-integral vector. If every component of a vector is either 0, 1, or 1/2, we see that the vector has a half-integral property. This is easy to understand. Lemma 1 shows that for any general graph, we can compute an optimal solution with the half-integral property of the LP in polynomial time. Based on the special optimal solution, we designed algorithm 1. The following algorithm 1 is our main result. We can reput a weight graph. Step 1. Compute the optimal solution of the LP with the half-integral property, and the optimal dual solution. Step 2. Based on the half-integral optimal solution, classify the verticide as follows. We refer this verticide as the first type of verticide, the second type of verticide, and the third type of verticide. Step 3. Compute this special edge site. Step 4. Calculate the maximum degree of the vertices in the graph. Step 5. Classify the players and allocate the cost they should bear. Finally, output this vector. It can be proved that the vector output by the algorithm is the allocation in the 2D over 1 plus d core of the minimal vertex cover game, which is our theorem 2. To prove theorem 2, we also prove some lemmas. To make the following understanding easier, let's first define some notations. Given a graph G and vertex subset A and B, NV denotes the set of neighbors of vertex V in the graph, while NB represents the set of vertices that are adjacent to vertices in B but not part of B. NAB denotes the intersection of vertex set A and the set NB. First, we study the structure of the subgraph generated by the second type of verticide and obtained the following properties. It may be more intuitive to explain this with a graph. Using the LP's optimal solution with a half-integral, we divide the verticide into 3 parts. The first type of verticide, the second type of verticide, and the third type of verticide. The second type of verticide is further divided into parts. On the left, we have the minimal vertex cover of the subgraph generated by the second type of vertices, and on the right, we have the other vertices. This lemma aims to show that vertices with the blue feature in the graph cannot exist. Based on these results, we can further derive lemma 3. By applying lemma 2 and lemma 3, we can complete the proof of theorem 2. Finally, we found tight exam that demonstrates our result is optimal, based on the maximal degree of the vertices in the graph. After introducing our work, let's move on to the final section, further work. A natural direction is to extend our research approach to other models such as independent set games. Alternatively, characterize the approximate core with other parameters in the graph. That's all for my report. Thank you.